All right, we're going to keep going with our work on patterns and nonlinear functions, looking at a challenge in a real-world connection problem. This problem is one of my favorites because it's really counterintuitive, and it connects to something that you could easily just model in the real world really simply with a piece of paper. So here's the scenario. I fold a piece of paper in half, and then I do it a few more times. After each fold, I count how many layers thick it is. And our task is to create a table, a graph, and a rule or an equation to represent this scenario. By the way, I think there's a myth out there that you can only fold a piece of paper in half 7 times maximum, maybe. And I think Mythbusters tried to bust that myth. I don't know if they were successful or not. So you should check out that video and see how I think they did it with a giant piece of paper that filled a garage or something. Anyway, let's tackle this problem here. I think you can realize that after 0 folds, just with our start, we just have 1 piece of paper, and then we could fold it. Let's try to go 1 past the 7 limit here, and we could fold it up to 8 times, or we could hypothetically fold it more. And I think you can see that each time we would have double the thickness. Okay, 16, 32, 64, 128, and 256. Okay. By the way, 256 layers thick is about half of a ream of paper. One of those packs of paper that you buy, I think, normally has 500 sheets. So we're about half of that just by folding 8 times. And let's go ahead and graph number of folds. I think you can tell that this is definitely a non-linear pattern. Things start increasing so quickly. And this is number of layers. And let's make sure we get up to about 250 here. So I'm going to go up by, let's go up by 40s every other. So every square is 20, 80, 120, 160, 200, 240, and then 280. Let's plot our points. If you didn't know already, that this is a classic example of exponential growth. And exponential growth is really notorious for starting out really, really slow. And then, you know, it's starting so slow, it's hard to get all these points down so close to the x-axis. 3, we're at 8. 4, we're finally a little bit of ways off the x-axis. But then, once exponential growth takes off, it really just takes off. And I think you'll see that here. 6, we have 64. 7, we have 128. And 8, we have all the way up here at 256. Roughly in there. Okay, so this is classic exponential growth. It starts out pretty flat, pretty slow growth, but it just keeps doubling, keeps doubling, keeps doubling, and eventually it grows just incredibly fast. Can you imagine with our 9th fold, we'd have 512, we'd be way off the screen. All right, let's try to come up with an equation. And one thing I've shown you with some of our other videos is to try to determine the slope. And let's do that here. So this is times, well, often I ask you to subtract. This is +1, this is +2, this is +4, this is +8. Are you seeing that we're just actually duplicating the original pattern? Okay. This pattern here, the pattern of our change, is the same as the pattern of the actual values in our number of layers. Okay, so that's just going to keep going forever. That doesn't really help us necessarily with an equation. So it's definitely not going to be linear, and it's not going to be quadratic either. But here's what we can do. I think we can see that it's just times 2 each time, right? Okay, so every time we're doubling. And so this is classic exponential growth, and that is going to look like an equation with this form. Start times the change to the x, okay? So we're going to get an equation that looks like this. 1 times 2 to the x. Okay, and then you can see, here's a good challenge for you. How many layers thick will it be if you could somehow magically fold that paper 50 times? And then go look up how thick a piece of paper is and see how tall that stack would be. Okay? That's a good place to stop right there.